This is the assignment 902.3 work energy theorem problem set, and I'm going to work through these questions one by one and hopefully answer any questions you guys might still have. Number one on mine says, in the roller coaster pictured, the roller coaster begins moving from rest at point A and accelerates downhill to point B. It then climbs back up to point C before plunging back down to point D and using a chain lift to make it up to point E. On this roller coaster, the cars move fastest at point B. Which of these is a possible correct explanation for the speed being fastest at point B? So if we look at this roller coaster, point B should not be the fastest point on this roller coaster. If we are thinking about this in terms of conservation of energy, at point B, we would still have some amount of gravitational potential energy, and so the energy at that point would be split between kinetic energy and a small amount of gravitational potential energy, whereas at point D, all of the energy at that point should be kinetic energy, which means that it should have more kinetic energy than point B does, and thus a faster velocity. So the question is, why is point B faster than point D? What could cause your roller coaster to lose energy so that it's moving slower at point D? And the only answer here that's going to make sense is that there's friction. If there's friction along this roller coaster, and maybe there's a lot of friction on this hill, okay, between B and C and D, we don't know, then that friction would cause that external force doing work on the system would cause your system to lose energy. And if you lose energy, you would of course have less total energy and thus potentially less kinetic energy at point D than you had total energy at point B. And so that's the only explanation here that makes sense, is that the roller coaster must be experiencing friction, causing it to lose some of its energy. These other answers, it can't be frictionless. If it were, D would be fastest. The next one says B is fastest because the cars have the most GP at point A and it's converted entirely into KE at point B. Again, that's also not true. We still have some height at point B. From A to D, that should be a true statement, but not at B. And then this last one is just a random throwaway answer. Don't fall for it. You're not creating enough new energy. Okay, it's simply taking the same total amount and it's just dividing it up differently at these different points. So there is no new energy created. And so you wouldn't want to select this. The only one that makes sense is the roller coaster must be experiencing friction that is causing it to lose some of its energy to the surroundings in an open system. The next question, question number 2, says a ball is launched straight up into the air and falls straight back down to its starting position. The ball is launched with an initial kinetic energy of 280 joules. If it encounters air resistance, how will the final kinetic energy compare to the initial kinetic energy? And so it's talking about the initial being launching it straight up and the final being when it falls back down. And so if we're at the same height, we would theoretically have the same amount of kinetic energy unless there's an external force doing work on our system. And in this question, there is an external force doing work on the system, air resistance. That air resistance should cause that ball to go to a shorter height, which means that it won't be falling as fast, and even as it is falling, that air resistance should slow it down. And so the final velocity of the ball should be slower than the initial velocity of the ball, meaning that the final kinetic energy should be less than the initial kinetic, or initial kinetic is greater than the final kinetic energy. Question number 3 says a 270 kilogram bobsled is pushed from rest along a horizontal surface by 2 athletes until it reaches a speed of 9.7 meters per second. Write the energy transfer equation for this scenario. Guys, you have to be able to write these energy transfer equations in order to get questions like this one correct. So you need to ask yourself, what form of energy do I have initially? What form of energy do I have at the end? Is there any work being done? And then you need to set up your equation. Sometimes it's easier to start with the end. And so if I read this, I know that at the end of this whole scenario, my bobsled is moving 9.7 meters per second. That's kinetic energy. So I know that the final state, I have kinetic energy. There is no mention of it moving upward. In fact, it even says that it's on a horizontal surface. So I don't have any height, and therefore I don't have any gravitational potential energy. Nothing is elastic. There's no mention of friction in here. And so the energy I have at the end is just kinetic energy. It's this 9.7 meters per second, this motion. So where did this energy come from? Because the law of conservation of energy states that energy can't be created or destroyed. We have to have the same total amount of energy initially as we have at the end. And so this energy has to come from somewhere. Again, it says it's a horizontal surface, so it didn't come from it rolling down a hill or something like that. Although that is a possibility in a different scenario. You could absolutely have something that takes gravitational potential energy and turns it into kinetic. That's just not happening here. Okay, but that's one possibility. It does say that it's pushed from rest, so I know that it didn't always have this kinetic energy. It started out with 0 kinetic energy. It started out with 0 gravitational potential energy. There's no mention of anything elastic. So where did the energy come from? It came from this. The bobsled is being pushed. There's a force doing work. So the work done by the runners, the athletes pushing it, is going to give us the kinetic energy we have at the end. That is your energy transfer equation. Work equals KE. This is the the work energy theorem. All right, so the next question says, what is the kinetic energy of the bobsled at this speed? So we're going to solve for the kinetic energy using the kinetic energy equation, which is 1/2 mv squared. And so we're looking for what the energy is. We have the mass, it's 270. We have the velocity, it's 9.7. And so that's what it looks like when we actually go to plug in. And then we're going to type this into our calculator. So 1/2 of 270 times 9.7 squared is going to give us a kinetic energy of 12,702.15. Now, I do want to caution you with this. If you are using a TI Nspire, then you may or may not be actually getting the same answer as I am. And it's not because the calculator is wrong or something like that, but it is because of a setting on the calculator. Okay, so let me show you what I'm talking about. Let me try it on this one and see if I get something different. 0.5 times 270, times 9.7 squared. And let's see if this one does what I think it's going to do. Yep, it sure does. Exact same thing, different answer. This one is chopping it off to 12,702.2 instead of 12,702.15. MyOpenMath will count this wrong. On a test, it's not really going to matter, but MyOpenMath, you have to go to 2 decimal places. So what you have to do is you have to adjust a setting in this calculator. So what you're going to do is you're going to push this dock button, and then you're going to choose option 7. So I'm trying to get the glare off the screen. There we go. Settings and status, and then option 2, document settings. And it's actually the display digits, the very first menu where it says float 6. That's only allowing me to have 6 digits. I would rather it keep every single digit displayed. So I'm actually going to go all the way up to the top where it's just float. And if you do that, and then you have to click OK at the bottom. If I can get this mouse over here. Then I can type in that exact same thing that we just had. Sorry, it didn't work. Okay, let me just retype it. All right, 0.5 times 270 times 9.7 squared. Oops. And now I have my decimals. Okay, so again, you might have to change the setting on the calculator. I don't want you guys missing this because of the Nspire. So just be aware of that so that you're not running into that problem. Or if you're using your own calculator, you're not going to have that problem, but the Nspire, for some reason, defaults like that. So let me type this in, 12,702.15. My unit will be joules. All right, what is the work done on the sled to accelerate it? Well, I do have an equation for work that says that work equals force times displacement times cosine of my angle if I have an angle. There's no mention of an angle, so I'm just going to do this. However, there's no mention of a force or a displacement either. So this is not going to work for solving for work. Instead, you're going to use the work energy theorem, which states that the work done is equal to the change in the energy of the system. And I know the kinetic energy now is 12,702.15, and I know it was initially 0. So the change in energy is actually equal to that final energy, 12,702.15, minus that initial energy of 0. Because again, it says it was at rest right there in the question. So my work is actually the same exact value as my kinetic energy. And again, that's what my equation says up here. Work equals KE. So that's going to be that 12,702.15 again. The units for work are the same as our units for KE. And then last question says, if the athletes push with a force of 180 newtons, what distance was the sled pushed to get up to speed? Well, now I get to use this equation. Because I know the work and I know the force, I can solve for the distance. So we're going to take our answer, 12,702.15, and we're going to set it equal to the force, 180, times that distance, which means we're just going to take our answer and divide it by 180. Which is equal to this value right here. 70.5675. I only need 2 decimals, so I'm going to round that to 70.57 meters. All right, so looks like we got those all right. Let's look at the next question. Question number 4. Question number 4 says, a book is sliding across the floor. It comes to rest after traveling 0.6 meters due to a friction force of 22 newtons. Write the energy transfer equation for this scenario. Again, it might be easier to start at the end, but we need to think about the forms of energy that are present at the initial state and at the final state. And at the final state, it tells me it comes to a rest, which means I don't have any energy. Okay, initially though, I have this book that is sliding across the floor. So this fact that it's moving tells me that I initially have kinetic energy, and that kinetic energy is going to be entirely dissipated from my system due to the work done by friction. So this is actually kind of a little bit weird way to write this equation, because I'm going to write it as KE equals work. But technically, we typically would write this as either KE equals dissipated energy or KE plus work equals 0, where the work is negative. Okay, so technically it's KE minus work equals 0, but if you rearrange that equation, you get this one, KE equals work. Honestly, this is not the question I'm most worried about you getting right on here, because it's hard for my Open Math to score this. I'm more concerned about the fact that you're able to write an equation and then use it to solve these questions. So let's go ahead and see if we can do that. We have our equation now, and it says, what is the work done by friction to make the book come to a stop? Again, we have a work equation right here. If we want to know work done by friction, we just need to do force of friction times the distance that it travels. In this question, it tells us that we have a friction force of 22 newtons. And so I'm going to label that as negative 22, because I know friction is always opposite the direction of my motion. And so I know that if my displacement is 0.6 meters forward, that my friction's got to be negative 22, because it has to be opposite the direction of this. So I have negative 22 times 0.06, and that's going to give me my work done by friction. And again, that's this equation here. And so if we multiply those numbers, negative 22 times 0.6, we get negative 13.2. And so that's going to be our work, negative 13.2. And again, our unit is joules. What is the initial kinetic energy of the book? And this is why I don't really like the equation written this way, because these aren't actually equal to each other. They're technically equal and opposite. This is a better way to write the equation, KE plus that work done by friction equals 0. because at the end I don't have any energy at all. And so I would be technically adding this negative 13.2 here, which means this has to be 13.2. They are equal in magnitude, but this equation sets you up to get the wrong sign. So just a warning with that. You could also write this equation as your kinetic energy is equal to your dissipated energy, and then recognize afterward that your dissipated energy is just how much energy is lost due to friction, and it's usually reported as a positive number, and so your KE is as well. So again, energy, you're not going to report it as a negative. It's 13.2. You had 13.2 joules of energy. You lost all of it due to the work done by friction. So here's how much was lost, 13.2. Here's how much you had, 13.2, and that's why you no longer have any motion. It's at rest. The last question says, if the book has a mass of 2.8 kilograms, what was the initial velocity of the book? Well, now that you know the kinetic energy and the mass, you can find the velocity using the kinetic energy equation. Again, that's this one up here. KE equals 1/2 mv squared. So let's go ahead and solve for that. Our KE is 13.2 equals 1/2. Our mass is 2.8, and we're looking for that velocity. So that's your setup. Half of 2.8 is going to be 1.4. And so if I want to solve from here, I'm just going to divide both sides by 1.4. That cancels that. And I have v squared is 9.42857. It keeps going, but I want v, so I'm going to take the square root of my answer, and I'm going to get this as my final answer, 3.070597894. Again, I don't need all those digits. I am going to just write down two of them, 3.07. That is correctly rounded. Check and make sure you're rounding right. This is question number 5 on 902.3. It says a spring is compressed, launching a 5.4 kilogram toy car along a track as friction applies a force of 21.7 newtons on the car for 3.8 meters. If the car is traveling at 8.3 meters per second after this, how much elastic potential energy was used to launch the toy car? Again, you have to be able to write your own equation. So let's think about what energy forms we have. I know that there's a spring here. I mean, you could even draw a picture of what's happening. So I have this spring, and this spring is going to launch this car. So you have this like initial state where the car is a very pretty car, where the car is on the spring, and then after it releases it, now your car is moving. Okay, so it's like a before and after. Okay, but again, I know at this stage when the spring is being compressed, I know that I have elastic potential energy, but I also know that when it's released that the spring is going to do work on the car. But I have this elastic potential energy here. It depends on what it asks for, because it could ask for the work done by the spring, and that's going to be the exact same answer as the elastic potential energy that it has. Okay, but I have elastic potential energy, and I know I'm looking for that because it says how much elastic potential energy was used. Okay, and I know over here that I have a car that is moving at 8.3 meters per second, because it says so in the question. So I know over here that I have kinetic energy at the end. But again, the question is it moving as fast as it should be, or should it be moving faster than this? We don't actually have any energy to figure out, but the question does tell us that there's friction applying a force. Well, guess what? If there's friction applying a force, that means this car should be moving faster, but instead it's moving slower because of the work done by friction that's removing energy from our system. And that work happens before we get to this point. That work is going to go over here. So we're going to take that EPE plus any work that's done by friction, if there is any. It's entirely possible that your elastic potential energy equals KE, except that I know in this case that there is friction. Okay, if it was a question that says, is there friction? Well, you could set them equal and then check, do they match? But in this case, I know there's friction. And so that would be how I write my equation. EPE plus the work done by friction should equal the KE that we have at the end. So with that in mind, let's go ahead and see if we can solve this. The elastic potential energy is what we're solving for. So I am not going to plug in variables. I'm not going to put 1/2 kx squared because I don't want the k or the x. I actually want the energy. The work, though, I need variables for. Work is force times displacement. So I'm going to put those letters in, those variables in, and then KE is 1/2 mv squared. They didn't give me the amount of work. They didn't give me the amount of kinetic energy. Instead, they gave me a mass and a velocity and a force and a displacement. So now we can substitute in. EPE plus this work done by friction is going to be, it's going to be a negative force because it's friction. So negative 21.7 times 3.8 meters. Again, I'm getting those numbers from the question. So I am going to actually be subtracting this out because I do want to end up with less energy here than I started with because of that friction. So it really becomes a subtraction problem. 1/2, again, my mass is 5.4 and my velocity is 8.3 squared. Okay, so that's my setup. So let me go ahead and multiply what I can. 21.7 times 3.8, and I get this, EPE minus 82.46 equals, and then we'll do the other side, half of 5.4 times 8.3 squared. And I get this, 186.003. From here, if I want to solve for that elastic potential energy, I just need to add this number to both sides. Because again, it was negative work, it was subtraction. Now we're going to add it to move it. And when we do that, we get this number right here. This would be your elastic potential energy, 268.463. All right, question number 6. Question 6 says, Mr. Smith uses 60 newtons of horizontal force to push a 26 kilogram physics cart from rest for 12.9 meters in 3.3 seconds. It then rolls up a 1.8 meter high ramp. How fast does the cart move once it's atop the ramp? So there's a couple different things happening here. We have Mr. Smith pushing this cart, and so we have a force here that's being applied to this cart. Okay, at the end, we know that after he pushes it, we know that this cart is going to go up a ramp, and so it's going to end up here, and it wants to know how fast it's moving once it's at the top. So I guess I should have drawn that differently, but once it's at the top of the ramp, so it's really asking about it once it's up here. Okay, but it's moving up the ramp, and then it's theoretically still moving once it's up here. And so that's the question, is how fast is it moving? We really don't care about this intermediate point. I should have probably not drawn that one. We really care about this point right here. Okay, and so if we think about what energy forms the cart has here, this cart is moving, or at least it's implied that it's moving because it says how fast is it moving. So we're assuming that there's kinetic energy. We also know that we're on top of a ramp, and so we know that we have height, which means we know we have gravitational potential energy. Okay, and so I know I have those two things. Where do these energies come from? Because again, conservation of energy, your total initial energy should equal your total final energy, or if you add in some work, then your energy plus work will equal your final energy. But this is my final right here. Okay, so what happens here? Well, here, it's not moving initially, it's actually at rest. In fact, he pushes it from rest. And the information it gives me is about his push. He pushes it for a certain distance, which means he does work on the cart. And yes, his work makes the cart move. And yes, the cart would be moving here and any point in between. And it is going to get slower up here, but I don't care about all these intermediate points. I could solve for them if I needed to. I don't. Okay, I'm going to save myself some time, and I'm just going to look at my initial point and my final point, and that's it. I'm going to write my equation. The work that he does is equal to the kinetic energy that the cart has at the end plus the gravitational potential energy it has at the end, because he doesn't just make it move, he also makes it go up a ramp. So it has both of these two. So again, plug in the variables. They don't tell me the work. They give me a force and a displacement. So I'm going to set that equal to, they don't give me a kinetic energy, or they don't ask for it, they ask for how fast. So we want that velocity. Let's put those variables in, 1/2 mv squared. And then again, they don't give me a GPE, they instead give me a height of this ramp. So we need to put the variables in. From here we can plug in some numbers. And so we have this 60 newtons of force that's applied for 12.9 meters. And that is going to cause this cart, which has a mass of 26 kilograms, to move, but we don't know how fast. We're going to solve for that while it's on top of this ramp. And so again, that 26 times 9.8 for gravity times the height of the ramp, which is 1.8. So that's your setup. So let's go ahead and solve what we can. 60 times 12.9 is 774. This is going to be 13v squared plus 26 times 9.8 times 1.8 is 458.64. Okay, algebraically, you cannot add these. They are not like terms. Please don't try. Instead, we're going to get this by itself by first subtracting this 458.64 from both sides. So if we subtract, it's going to cancel it on the right, and on the left, it's going to leave us with this. 315.36 equals 13v squared. Again, I still need to solve for this v. I need it by itself. We're going to divide both sides by 13. That's going to leave us with 24.26. I'm rounding this. Equals v squared, and again, I don't want that, I want the square root of that. And so what we get when we take the square root for that velocity is this number right here, 4.92528. It keeps going. I only need 2 decimal places, so 4.93 is how that would be rounded. Question number 7. Question number 7 says, Mr. Boyd applies a horizontal force of 3.5 newtons to pull a 2 kilogram box initially at rest, a horizontal distance of 8.2 meters. The box's final velocity is 4.8 meters per second. So I know that I have this box and that it's going to be pulled. It's initially at rest, and then after he pulls it, now it's moving at 4.8 meters per second. I know that when he pulls it, that he uses some amount of force, specifically 5.3 newtons, and then he does so for a certain distance. So they gave me the force and the distance. I know at the end it's moving, I have kinetic energy. Again, sometimes it's easier to start at the end. So I have kinetic energy at the end. There's no mention of height, there's no mention of anything elastic. Okay, there is mention of friction though, how much energy was used to overcome friction. Okay, so we are going to need to take that into account in a second, because that implies that there might be friction. However, it is also possible that the work he did, again, it gave me a force and it gave me a displacement here. He's doing work. That work that he did could be equal to the kinetic energy at the end. Or they could be 2 different numbers, in which case you would have energy that had to be used to overcome friction. And that's the question. So you could, again, the actual equation is usually net work equals KE in this case, because there are 2 different things doing work. There's the work done by Mr. Boyd, and there's the work done by friction. And those 2 together could equal this. Or you could write the equation, the work done by the man equals the KE, and see if there's a difference and look for that dissipated energy. These are 2 different ways of writing the same thing. You're going to get the same answer no matter which way you do it. Okay, I'm going to use this one since it's at the bottom right now, but again, either one works. So the work done by Mr. Boyd, it says that he applies a force and it gives us a distance. So we actually don't want work, we want his force times his distance for Mr. Boyd, plus again that work done by friction equals the kinetic energy at the end, which is 1/2 mv squared. Now again, the question's not asking me for the force of friction, it's not asking me for the distance or anything like that. It wants to know how much energy was used to overcome friction. So I'm not going to substitute variables in, I'm going to leave it like this. I could, if I wanted to, write change in energy due to friction, because it's the same thing. But let's go ahead and plug in some numbers. So we know that his force is 5.3 newtons. We know that the distance that he pulls the box is 8.2 meters. And then we know that the box has a mass of 2 kilograms and that after he pulls it, it's moving 4.8 meters per second. And so that's what we're going to get for our setup. So let's go ahead and solve for this. 5.3 times 8.2 means that my initial work that he did is 43.46. So that's his work. Over here, how fast it's moving, 0.5 times 2 times 4.8 squared is 23.04. So if you had solved it in steps and said, okay, here's his work, okay, here's the KE, are they equal? You'd already know they're not. And you would know that you could subtract to find the difference. This is already building it into the equation. If you had used this equation, you would just be building it in on this side instead of this side. It's going to give us a different sign, so just a heads up, but I'm solving for work done by friction. If I were solving for dissipated energy, I would get a positive. I'm about to get a negative number. I'm not going to type that negative though, because this question is asking how much energy was used to overcome friction. And we're not going to have a negative number here for this. So I'm just going to report the magnitude of it, but you're going to get the same answer. So I'm going to subtract my two numbers. And that's going to give me the work done by friction as negative 20.42, but the amount of energy used to overcome that friction, again, you're just going to report the magnitude, is 20.42 joules. Question number 8 says, Mr. Shell drops a 1.9 kilogram pendulum bob from a height of 3.6 meters at point V. It swings up and back down, and its velocity is found to be 6 meters per second at a height of 0, which is going to be at point X. How much energy is dissipated from the system when the pendulum moves as described? So again, we're going to need to think about the energy forms that are present. I know that this pendulum bob, it tells me about what's happening at point V, and at point V, it's dropped from rest. It says he drops it. It doesn't say that he throws it or pushes it. He was holding it and he dropped it. So at point V, we know that we have gravitational potential energy at the top of the pendulum. At point X, which is the point that it's asking about or giving us other information about, at point X, it's at a height of 0. And so I know that the only energy present here is KE. So again, the question is the GPE that it has here equal to the KE it has here? Because this is my total energy. My total mechanical energy here is gravitational potential because there is no kinetic. My total energy here is kinetic because there is no gravitational potential. If we had picked one of these points in between, W or Y, you'd have a little bit of both, but we don't. And so the question is, are these equal to each other? Or is there friction? Because that's the question. How much energy is dissipated from the system? That answer could be 0. If these are equal, it is 0. Okay, so we can solve it in steps like that and see if they're equal. And then if they're not, again, or we could even include this. If they're not, then you're going to get 0 for dissipated energy. Again, the last one I worked out using the work equation, I'm going to use dissipated energy for this one. Whichever one you like better is fine. You're going to get the same answer. So my gravitational potential energy, again, we're going to use mgh equals, again, instead of KE, we're going to use 1/2 mv squared. And then again, if those are equal, we don't have friction. But if they're not, we're looking for the dissipated energy. And it's possible that this is 0. So let's see if it is. If we plug in our numbers, we have 1.9 times 9.8 times the height of that pendulum bob at point V is 3.6 equals 1/2 times that same 1.9 mass times the velocity it gave me, which is 6 squared. So let's go ahead and multiply out these numbers and see if these two things are equal or if we need to solve for that. Okay, so 1.9 times 9.8 times 3.6 gives me an initial gravitational potential energy of 67.032 joules. So that's how much GPE we have. Okay, let's see if it's equal to the KE. This is what that calculation is. 0.5 times 1.9 times 6 squared. And we get this, 34.2. So very obviously those are not equal. Very obviously we have dissipated energy. We lost a bunch. We had 67, we have 34. We lost a bunch. So how much did we lose? Again, you find it by subtracting. When you subtract those numbers, you're going to get 32.832 joules, which is your answer. Now again, this question is asking how much energy is dissipated. The way that the question is worded is implying that that there is energy loss from the system. You don't have to type the negative. In fact, don't type the negative. If the question had said how much work is done by friction, then yes, you would need to label it as a negative because that work would then indicate that it was lost. But it already indicates that with this word right here, dissipated. So I'm not going to type a negative sign. Report my answer is just 32.832 joules. Submit. All right, question number 9. It says, Fernando decided to go snow skiing over his holiday break. On one of the ski slopes, he starts from rest on top of a 23-meter tall hill and skis into the valley and back up onto an 11-meter tall hill. Guys, I'm going to really strongly encourage you to draw a picture for this particular problem so that you can better visualize what's happening. So we have this skier that goes on some kind of track, slope, whatever, that looks like this. Okay, it says that they're at rest up here. Okay, so my initial velocity is 0 up here, and they're going to go down this hill and then back up this smaller hill, because this one is 23 meters high, whereas this one is only 11 meters high for measuring them from the same baseline. Okay, and so I have some heights here, and at the top of this hill, it says that, let's see, it says he goes back up onto it, so we would assume that he's still moving. Then when he's on this hill, it says he uses his poles to do work to push himself along an 8-meter long stretch of snow. Okay, so there's going to be work that's happening here, work. Okay, and so after that, now he's over here. Okay, after that he's traveling 20.7 meters per second. Okay, how much force did he apply for that stretch of his trip? So that work again happens over this 8 meters. All right, so he should be 20.7 meters per second is theoretically faster than he would be traveling otherwise because he did positive work. He added energy into the system, so this is faster than it should be. Okay, if you're going to write the equation, again, it might help to start with what you have at the end. Okay, at the end of this, we're just looking at this point here. Okay, that's at the end. And so at the end, we know we have kinetic energy, okay, because he's moving. But we also still have height. We're still on top of this hill. It says that he's on a horizontal stretch on top of the hill. So we have GPE and KE up here. Okay, initially, when he starts here, he has no velocity, so he doesn't have any KE, but he does have height, so he has GPE initially. We just said a second ago that this energy he has here is more than it would be if this hadn't have happened. Because this happened, we have to add it in. This happens before this. So we have to say, hey, this energy he had up here plus this work that he did is how he ends up going this fast, because he shouldn't be that fast. Okay, it's only because he added work, okay, to the system in order to increase his speed here so he has more kinetic energy. So my equation looks like this. GPE initial plus work equals KE final plus GPE final. Some of you guys are having a really hard time with this question. Okay, and I'm not sure if it's because of where the work is mentioned in the story, but it doesn't matter. It happens before this final state, so you're going to add it to whatever you had initially in order to get this. Okay, beyond that, we always put work on the left-hand side of that equation, or at least we have been. Even when it's friction, we've been writing it as work here, and it ends up being negative, but this time it's going to be positive. We don't typically label it over here, although we have labeled dissipated energy over there. Which is not the same thing as what's happening here, because this isn't dissipated, this is positive, so it has to go on this side. All right, so again, we don't have these things, we have instead these variables, MGH plus the work here. I don't want to list it as work because the question tells me that it's asking us for the force that he applied doing this work, so I'm actually going to substitute in these variables also. Force times distance equals 1/2 mv squared plus mgh. So that's my substitution step. My skier has a mass of 68 kilograms. Gravity is 9.8. The height of the first hill is 23 meters. Plus the force that he uses is what we're trying to solve for. That's what the question asks. How much force did he apply? So F is my variable. But I do know how long he applied the force. It was for an 8-meter stretch. Equals 1/2. The mass is still 68. The velocity at the end is 20.7. And again, same mass, gravity is always the same, and the height at the end is 11. Okay, so that's my setup. Now, you could actually leave this as work, solve for work, and then do the extra step with the work equation. That's fine. But just like you can substitute these variables in for these guys, you can substitute these in for this. So if you want to do it all in one step, here's how. So let's go ahead and solve what we can. 68 times 9.8 times 23 is going to be 15,327.2 plus 8F. And then on this side, I'm going to solve all this and add it together. And I get this number, 21,899.06. Look, here's how much gravitational potential energy he started with. Here's how much energy, total mechanical energy, has at the end. So my mechanical energy has increased. And again, it increased because he did work. He added energy to the system. Okay, and so we're going to figure out not how much work he did, but rather how much force he applied. Because again, that's force times distance right here. So we're going to subtract first. 21,899.06 minus that 15,327.2, and we're going to get that work that he did, which is what this is work, is force times displacement, is equal to 6,571.86. So there's the work, but we want the force. So let's divide both sides by 8, and that'll give us the force that he applied, which is going to be equal to 821.48. That value right there. All right, last question, and this for some reason was the hardest for most of you guys. If you had issues, it seemed to be overwhelmingly with this problem. It says, Miss Darwin plunges from rest off of an 88-meter high bungee platform. I'm going to draw a picture. If you didn't notice that in the last one, that theoretically helped you. So we know that we start out up here on top of this platform that is 88 meters high. Okay, at her lowest point, when the bungee cord is at maximum extension, Miss Darwin is 7 meters above the ground. So whenever we jump off and we're on our bungee cable, okay, now at the end, we're going to call this 7 meters. Okay, and so our bungee cable will be holding us up, okay, from that point. Okay, and so it says if her mass is 84 kilograms and the bungee cord has a spring constant of 52.88 newtons per meter, then what is the resting length of the bungee cord before it stretches? Assume no friction. So here's the deal, and you can kind of see it in my picture. The total length of the stretched cord plus the height I have above the ground equals 88. Okay, and so if we want to figure out the total length of the stretched cord, it's just going to be 88 minus 7 with the numbers I have, which means that the stretched cord has a length of 81 meters. Okay, because that's this distance here. Here's how high I'm above the ground. That's how high we started. Okay, this is not your answer. Okay, because this doesn't ask what the stretched length is. It wants to know the resting length. Okay, when you have something that's stretched out, we looked at it with springs mostly, but you have like this resting length, and then you have your stretched length, right? Right now I know this. The question wants to know this. The difference between these two lengths, when we talked about elastic potential energy, this difference here is the deformation or displacement of the spring. It's the X value. So what that means is we need to figure out what the X value is, how much it got stretched by. Because if we can find that, the resting length plus that stretched amount, that X value, is 81. Okay, so because this is our stretched cord down here. So anyway, point being, this is in my elastic potential energy equation. So that needs to show up in my equation. Let's go ahead and see if we can write an equation. It gives us information about this initial state up here when we're on top of this platform. And on top of that platform, we have GPE, and that's it. We're not moving yet. There's no stretched cord. We just have gravitational potential energy at that point. Okay, the other point that they give us information about is this point here. At this point, we have stretched a cord, so we have elastic potential energy, but we still have height. We have 7 meters of height. And so we have gravitational potential energy as well. This question tells us to assume no friction, so we're going to say that the GPE we start with equals the EPE plus the GPE that we end with. Because when the cord is fully stretched at its maximum extension, we wouldn't be moving. That would be when it fully stretches and before it flings us back up. So you have to stop for a split second. So your equation looks like this. The GPE at the top equals the GPE at the bottom plus the EPE that it has at the bottom. And again, we don't have these energy values. We have variables. mgh equals mgh plus 1/2 kx squared. So let's substitute in to that equation. The mass, it says, is 84 kilograms. Gravity is 9.8. The height of the platform is 88 meters. Again, mass doesn't change, gravity doesn't change, but the height at the end, it tells us that height is 7 meters above the ground, plus 1/2. It gives me a spring constant of 52.88, and then x squared. Running out of room. Okay, and so that is the substitution step. So let's go ahead and solve that left-hand side first. 84 times 9.8 times 88 gives me a gravitational potential energy initially of 72,441.6. At the end, the gravitational potential energy is 84 times 9.8 times 7, which is 5,762.4. And then half of 52.88 is 26.44x squared. Okay, so again, I cannot add these. They are not like terms. We're going to subtract this from both sides. So I'm going to take that giant 72,000 number and I'm going to subtract that 5,700 number, and I'm going to get this. 66679.2 equals 26.44x squared. If we want to solve for x, now we're going to divide both sides by 26.44 and then take the square root. And this is your amount of deformation, how much it's stretched by, 50.22, if I round that, meters. That is not your answer. It doesn't ask for that. It asks what the resting length is. All we did was find how much the change was in the length before and after. I already know the after, 81 meters. It stretched by this much. So before that, again, the resting length plus the stretch, which I'm going to call x, equals the stretched length. Okay, I already know this is 81. I know this now is 50.22. I can figure out what that resting length is. Okay, and so I'm just going to do 81 minus my answer. And that should be what we have to type in for our stretched length. 30.78. Okay, you have to think through it. Draw a picture if you need to, but you have to be able to reason through it. And you do need to understand what the values mean when you're talking about springs, okay, or elastic bands in this case. All right, so hopefully that helps with this assignment 902.3. If you still have questions, please make sure that you're coming in for tutorials.